The automotive world is in the midst of a dramatic transformation. The familiar rumble of the internal combustion engine is being challenged by the quiet whir of electric vehicles. This showdown is reshaping the future of personal transportation. A new challenger has entered the arena. The EV, with its promise of clean, efficient power, is rapidly gaining ground. This isn't just a battle of engines, it's a battle for the future of mobility. The internal combustion engine, a marvel of engineering, converts the energy stored in fuel into mechanical power. This process begins with the intake of air and fuel into the engine's cylinders. The piston compresses this mixture, creating a highly pressurized environment. A spark ignites the compressed mixture, causing a controlled explosion. This explosion forces the piston downwards, initiating the power stroke. This downward motion is converted into rotational motion by the crankshaft. This rotational force is then transmitted to the wheels, propelling the vehicle forward. The engine's efficiency and performance depend on the precise synchronization of these components. The roar of an ice is the sound of controlled explosions, a symphony of power. The computer system in a traditional ICE vehicle, while complex, is generally simpler than its EV counterpart. The engine control unit, or ECU, is the brain of the operation, constantly monitoring various sensors throughout the engine. These sensors provide data on factors like air intake, engine temperature, and exhaust gas composition. The ECU uses this information to adjust parameters like fuel injection timing and spark ignition. This ensures optimal engine performance and minimizes harmful emissions. It's a robust and reliable system honed over years of development and refinement. The IC's computer system is the unsung hero, ensuring smooth and efficient operation. Electric vehicles rely on electric motors to convert electrical energy into mechanical power. Unlike ICEs, electric motors operate silently and produce zero tailpipe emissions. Permanent magnet synchronous motors, or PMSMs, are known for their high efficiency. They use permanent magnets, reducing maintenance. Induction motors are robust and simple. They are less expensive to produce. Electric motor technology advances rapidly, driving EV innovation. The computer system in an electric vehicle is more complex than that of an internal combustion engine vehicle. It manages the electric motor, battery pack, charging system, and other functions. The battery management system, or BMS, monitors the battery pack. It tracks voltage, current, and temperature for safe operation. The BMS also manages charging, optimizing battery life. The computer system controls power electronics for the motor. This allows for regenerative braking, capturing energy during deceleration. Electric vehicles offer flexibility in motor configuration, ranging from single motor setups to quad motor systems. Single motor EVs are typically front-wheel or rear-wheel drive, offering a balance of performance and efficiency. Dual motor setups introduce all-wheel drive capability, providing an enhanced traction and performance. By independently controlling the power delivered to each axle, the vehicle can optimize its handling and stability in various driving conditions. Tri-motor configurations further enhance performance, allowing for even finer control of power distribution. Quad motor systems represent the pinnacle of EV performance, offering unparalleled control and traction. Each wheel receives individual power control, allowing for precise torque vectoring and dynamic handling capabilities. Thermal management is crucial in EVs, ensuring optimal performance and longevity of the battery pack and motor. EVs employ various cooling methods to regulate the temperature of these critical components. These methods include liquid cooling, air cooling, and refrigerant cooling. Liquid cooling is the most common method, circulating a coolant through channels within the battery pack and motor. This efficient method effectively dissipates heat, maintaining optimal operating temperatures. Air cooling, a simpler approach, utilizes fans to circulate air around the battery pack and motor. While less effective than liquid cooling, it's a cost-effective solution for EVs with less demanding thermal requirements. Refrigerant cooling, similar to air conditioning systems, uses a refrigerant to cool the battery pack. Effective thermal management is essential for maximizing battery life and ensuring consistent performance. ICE vehicles also require robust thermal management systems to handle the intense heat generated by combustion. The primary cooling system circulates coolant through the engine block, absorbing heat and preventing overheating. This coolant is then cooled by the radiator, dissipating the heat into the atmosphere. Another crucial component is the oil cooler, which cools the engine oil, lubricating the moving parts and preventing excessive wear. The oil cooler is essential for maintaining engine longevity and performance. The cooling system in an ICE vehicle is a closed loop, constantly circulating coolant and dissipating heat. Maintaining the correct operating temperature is crucial for ICE performance and longevity. The ICE versus EV debate isn't about declaring a definitive winner. It's about understanding the strengths and weaknesses of each technology. ICE vehicles offer familiarity and a vast refueling infrastructure. However, they produce tailpipe emissions and are less efficient. EVs offer zero tailpipe emissions, quieter operation, and instant torque. They also benefit from lower running costs. However, EVs face higher upfront costs and a developing charging infrastructure. The future likely lies in a combination of both technologies. As battery technology improves, EVs will become increasingly mainstream. Ultimately, the choice depends on individual needs and preferences.